Video we will continue our discussion with the frequency selective fading. So this is the standard expression of the channel impulse response. It looked like this, which is the function of the coefficient and the phasors and the propagation delay, and we represent phi and t by this form, which is a function of ft comma n and tau n. Now, since in this case we have multiple propagation delays, tau 1, tau 2 up to tau n, we will try to modify these expressions. So let us first take phi n theta t comma n tau. So this is just a modification where what we have done is we have substituted tau n with tau n tau, which represents tau from the first path, tau from the second path, and so on. And then if we try to substitute this expression into the standard channel impulse response, what we get is this h t comma tau, which is represented by this expression. Instead of phi n of t, we have substituted phi n theta t comma tau n. And on top of this, we also have a summation of tau n is equal to 1 to n tau max, which represents the number of ellipses or the number of propagation delays that can be resolved at the receiver. So when we try to expand this expression, what we get is this form, which is nothing but the channel impulse response at a time t arriving at a propagation delay tau 1. Then this one is arriving at a propagation delay of tau 2. So what we can see is the channel impulse response for a frequency selective fading is the addition of the impulse responses at different propagation delays. That means we can write this in this form: t comma tau is equal to channel impulse response at tau 1 plus impulse response at tau 2 and so on. Now to get the frequency response of this expression, we need to take Fourier transform of this expression. Now when we try to compute the Fourier transform, what we end up is the Fourier transform of h t comma tau 1. This is tau 1 and this is tau 2. And the Fourier transform of h t comma tau 2. So as if we can write the Fourier transform of h t comma k to be the Fourier transform of h t comma tau 1 plus the Fourier transform of h t comma tau 2 and so on. Now if we try to understand how this response look like, we will see this figure. So in this figure we have plotted against in the x-axis we have frequency k, and in the y-axis we have gain, that is the mod square of frequency response, and it is in dB, so we are taking 10 log 10. So now the interesting thing to note here is when the delay spread is 10 nanosecond, that is the delay spread is very small, and when an impulse is launched into the system, we receive echo. If this is the delay axis, we receive echo with a very small fraction of delay, and this is 10 nanosecond. And in this case we can observe that the frequency response is almost flat with change in frequency. And why this is so? Because this is very small. So this situation arises in the flat fading scenario, as if we only have one resolvable path. That is, we are only considering tau 1 to be equal to tau hat. So that is the condition for flat fading. So in flat fading, we can say we are achieving a frequency response that is constant with the frequency. Now when we try to increase the delay spread to 50 nanosecond, so increasing the delay spread means now the echoes that are coming, the impulse is not an impulse anymore. but it is delay in time. So this is now 50 nanosecond. So now this there has been spread. So because of this spread, what we achieve in the frequency response is there is some fluctuation of the signal with the frequency. So now earlier with the frequency the response was flat, but now when the spread has been increased, the response is not flat response. Instead, for some band of frequencies the response is flat, whereas for the other frequencies it is not flat. So that means we can say for some frequency there is a selectivity, certain proportion of the signal is getting passed, whereas the certain portions of the signal like this one and this one, they are getting highly attenuated. Now we further increase the delay spread to 100, means now we have even more delay spread. We are receiving echoes for a very long time. This is 100 nanosecond. So in this case, what we see is that the response is now being changed to this black line as shown in the figure. So here you can see that there is a proportion of even a smaller proportion of frequencies for which there is less attenuation, and a smaller amount of frequencies where there is heavy attenuation. So what we get is for this proportion, for this portion there is less attenuation, and also for this portion there is less attenuation, but whereas for this portion it is highly attenuated. So means we have a selection in frequency where the signal is passing with low attenuation, or we can say the signal is highly correlated, or there are some portions of the frequency where the signal is highly attenuated. Now if we further increase the delay spread to 1000 nanosecond, we get a there are many fluctuations in the response with respect to frequency, like in this green line. So with this we will define what do you mean by coherence bandwidth. So like coherence time, in case of coherence time we have seen that if this is the time axis and this is the signal response, so we have said that in this time the signal is highly correlated to itself. That means there is a selection of time where we can achieve a high correlation in the signal. Same definition applies to coherence bandwidth as well. So in coherence bandwidth, this is the frequency axis. So for example, in case of 10 nanosecond, we have this red line and this is flat. So the signal will remain correlated across all the frequency axes. So this means we can define this as the coherence bandwidth. Now if we further increase the delay spread, like in this blue line, so now with the increase in the spread has reduced the coherence bandwidth. Now this is the coherence bandwidth where the response is almost flat, or we can say the signal is correlated to itself, and this has been reduced with respect to the flat fading scenario. Now if we further increase the delay spread, as in the black line, we can see this is the time over which, or this is the frequency, this is the frequency over which the signal is correlated to itself, and this has been more further reduced compared to the delay spread of 50 nanoseconds. And now if we assume that we have a delay spread of 1000, in 1000 we can say this is the amount where the signal is highly correlated to itself. So what we have observed in this figure is that as we are increasing the RMS delay spread, the coherence bandwidth is getting reduced. So then we can say that we have an inverse relationship between the coherence bandwidth and the RMS delay spread. So we can write coherence bandwidth is inversely proportional to RMS delay spread. And ideally there are two formulas defined for coherence bandwidth. Coherence bandwidth of which have a 50% correlation of signal with itself is defined by 1/5 into tau RMS, and coherence bandwidth for 90% correlation is defined by 1/50 into tau RMS. So understanding this tau RMS and coherence bandwidth, we can easily characterize the frequency selective fading. And we have also seen from this figure that there are more fluctuations in the signal with respect to the frequency, and there is a selection of frequencies over which the signals are correlated, and there are selections over which the signal is not correlated or it is highly attenuated. So hence we call it as frequency selective fading. So now with this we have studied the small scale fading, that is the time selectivity and the frequency selectivity. In time selectivity, we understand what is slow fading and fast fading. So slow fading, when this coherence time is greater than, when this coherence time is greater than symbol duration. If this is the symbol duration, so we say that these 2 points are highly correlated. That means we have a slow fading scenario. And in case of fast fading, we said coherence time is less than the symbol duration. If this is the symbol duration, then we have a high fluctuations during the symbol duration. In flat fading, the coherence bandwidth is greater than the system bandwidth. Means if this is the system bandwidth, then we said that this is the coherence bandwidth over which the response is flat, and no doubt whatever system bandwidth you consider, the response will always remain flat. Whereas in frequency selective fading, we saw coherence bandwidth is less than the system bandwidth. Just you can imagine this case, this blue line, when the RMS delay spread is 50 nanosecond. If this is the system bandwidth of BS, then the coherence bandwidth has now been reduced. So this is the scenario for frequency selective fading.